Good day, my name is Tuilis Wanda. I'm going to be doing a presentation on fluid mechanics. Here I'll be talking about how to size your pumps and also the pipelines, the valves and stuff like that. That's for the future presentations. But for now, let's get going. So I'm going to talk about types of flow. Flow through a pipe can be classified as laminar flow, turbulent flow, or critical flow depending on the Reynolds number of flow. So this depends on the velocity of the fluid in a pipe. So laminar flow, which means it's moving slower, and then which means there's no mixing of particles within the water molecules. Whereas turbulent flow, we call it fully developed. Now the particles of the fluid or water, they're getting mixed. Then the critical is in between. So in turbulent flow, for example, if you put a dye in your water and you have a transparent pipe, you can see that dye being mixed. But whereas in a laminar flow, if you put a dye, then you have a transparent pipe, you could see your dye moving in straight lines, which means the water molecules are not mixed. So mathematically, if R represents the Reynolds number of flow, the flow types are defined as follows. So for Reynolds number less than 2100, we call it laminar flow. Then the critical flow lies between 2100 and 4000. Then the fully developed flow, which is the turbulent flow, your Reynolds number is greater than 4000. So pressure drop due to friction. As water flows through a pipe, there is friction between the adjacent layers of water and between the water molecules and the pipe wall. The same applies when you kick your ball on the ground. As it's rolling down along the ground, there's a friction between your ball and the ground. This friction causes energy loss to be lost. This friction causes energy to be lost, being converted from pressure energy and kinetic energy to heat. So as this flow, as the water flows along the pipe, which means there's energy loss. So which means since energy is conserved, energy is converted from one energy form to another, and I will show you as we go on with the presentation. The pressure continuously decreases as water flows down the pipe from the upstream end to the downstream end. The amount of pressure loss due to friction, also known as head loss due to friction, depends on the flow rate, properties of water, which are specific gravity and viscosity, pipe diameter, pipe length, and internal roughness of the pipe. So different material which make up the pipe level, different roughness. Bernoulli's equation. It is a form of the energy equation for liquid flow in a pipe. At each point along the pipeline, the total energy of the liquid is computed by taking into consideration the liquid energy due to pressure, velocity, and elevation combined with any energy input. For example, if you're pumping your liquid, energy output and energy losses. The total energy of the liquid contained in the pipeline at end point is constant. So which means the energy cannot be created or destroyed. It can only be converted from one form to another. This is also known as the principle of conservation of energy. So which means the particle at any point is the same energy. Here I have a diagram. Consider a liquid flow through a pipeline from point A to point B, as shown. It is assumed that the pipe diameter at A and B are different, so which means the diameters here and there are different, so that the velocities are different. Otherwise, if it's of the same diameter, then which means the velocity will be the same, right? And hence the flow velocity at NP will be represented by PA and VP respectively. The Bernoulli's equation, taking into account the addition of energy, such as from a pump at A, and accounting for frictional head loss, HF, is as follows. So we are saying we have a pump here which is inputting some energy, but also as this fluid is flowing along this pipe, it loses some energy, which we call it friction loss. So the resulting Bernoulli equation is like this, which means energy at point A is equal to energy at point B, using the conservation of energy. So the Bernoulli's equation has three components. It has the potential energy, it has the pressure energy, it has the kinetic energy. This is energy input, in this case a pump, and this is the energy loss. So where HP is the equivalent head added to the liquid by the pump at A, right, and HF represents the total frictional head losses between points and B, between points A and B. So what is the Darcy-Weisbach equation? It is used to calculate the pressure drop in pipes transporting any type of fluid, such as liquid or gas. So we use this Darcy's equation to calculate this HF. And why calculate this HF anyway? Remember, we want to size our pump. I mentioned when we started the presentation, we want to size this HP. How much should our pump, how much head should our pump have? As water flows through a pipe from point A to point B, the pressure decreases due to friction between the water and the pipe wall. The Darcy equation may be used to calculate the pressure drop in water pipes as follows. So H, which is the frictional pressure loss in feet of head, is equal to F, which is the Darcy friction factor, it is dimensionless, which means it doesn't have any dimensions. It is unitless. L is the pipe length in feet. D is the inside pipe diameter in feet. Then V is the average velocity in feet per second. Then G is the acceleration due to gravity, feet per second squared. And if you're using the other units, these are the values of your G, and but in SI unit is different. Of course, it's 9.81 meters per second squared. In order to calculate the friction loss in a water pipeline using the Darcy equation, we must know the friction factor, F. So in order for us to calculate this friction loss, frictional pressure loss, we need to know the F. Because length, usually you know the length of your pipe, you know the diameter of your pipe, you know the required velocity, or if you know your volumetric flow rate, then you can convert back to the velocity. So the only thing which you don't know is this F. The friction factor of F in the Darcy equation is the only unknown on the right-hand side. This friction factor is non-dimensional number between 0 and 0.1, usually around 0.02 for turbulent flow. That depends on the internal roughness of the pipe diameter, and the Reynolds number, and therefore the type of flow, is it laminar or turbulent. So for laminar flow, the friction factor F depends on the Reynolds number and is calculated as follows. So frictional factor is equal to 64 over the Reynolds number, where F is the frictional factor for laminar flow and R is the Reynolds number for laminar flow, which means your Reynolds number is less than 2,100. So I'll give you an example here. So assuming that we calculated our Reynolds number, we found that it's 1,200. It means that it's in the laminar flow regime. So if our internal diameter is 400 millimeters, then we know the required flow rate, which is 500 cubic meter per hour. So we want to calculate pressure loss per kilometer, assuming we know that our pipe length is 1 kilometer. So this is another form of the DAS equation when you're using the SI units. For most of us, we know we love the SI unit or we're taught in SI units. But I'll use, for this example, I'll use this version, which says pressure drop due to friction per kilometer is equals to 6.2475 by 10 to the power of 10 multiplied by Darcy friction factor, which is dimensionless, multiplied by the volumetric flow rate in cubic meter per hour, all over or divided by pipe inside diameter in millimeters. So you need to take note the units. Otherwise, if you make a mistake, you'll get a wrong pressure loss. Then your pump will be wrong. It will be oversized or undersized. So now, since we were told that the Reynolds number is 1,200, to use the formula F is equals to 64 over R, which is the friction factor, we get this value. So going back to this equation now, we plug in. Now we have our friction factor, we have the Q, we have the D diameter we're given. So we just plug them in. Then I get that I have a pressure loss of 81.3 kilopascal per kilometer. You see, it's very easy if the flow is stable, but in the industry and in most pumping of water, the flow regime is in the turbulent region. So if the flow is turbulent, which means your Reynolds number is greater than 4,000, calculation of the friction factor is not as straightforward as that for laminar flow, which means it becomes a bit tricky to calculate for your friction factor. But I'll discuss this on the next presentation. Now I'd like to thank you for watching my presentation. If you have any queries, additions, subtractions, feel free to contact me on my email address tubaspad@gmail.com. Also remember to like, comment, and subscribe to my YouTube channel to learn some lit engineering stuff. Thank you.